Some classification problems in machine learning are anomaly detection problems instead. I've, I've dealt with classification problems, and mm, most of the time, the, the top difficulty with them is the imbalance of the data. So we're trying, well, it's very famous, and many people talk about the ability to the paradigmatic problem of telling if an image if it's a cat or a dog. And okay, that sounds very interesting, and it's very good for a good starting tutorial. But it's not what we most of the times find in industry problem settings, or actually business driven value um, models. So this is this is not 50-50 chance uh, of classifying accurately or correctly. So most of the times we deal with things like uh, getting getting a payer in an advertisement setting where we uh, in internet advertising we probably are impressing million million different users for getting inside the funnel or getting uh, paid finally, or the user buying the product or doing a particular lead action. Uh, it comes very rarely. Most of the times, less than 1%, less than one per thousand. Sometimes we are talking about proportions of the desired outcome or the desired or the positive class, if we want to think about this in terminology of classification. Sometimes we're talking about parts per million, so parts in a million. So um, we're dealing many times. For instance, another paradigmatic case is fraud detection. And detection is a good part of the problem statement, because it's detecting, it's not classifying, it's not good or bad. It's trying to look, uh, find, and recall and retrieve the instances that we consider positive among a huge pool of possible candidates. Um, it's not by chance that, um, well, the term is not uh, very hyped now, but we used to call this data mining. Mining. One of the things is that we try to refine a lot of big amounts, a huge amount of terrain and mineral or soil. We deal with a massive amount of material in order to um, filter out a small part of it, which is valuable, which is the mineral or the gold. So when we're talking about producing gold or extracting gold as a mining operation, we're talking about, okay, how many tons of sand we need to move in order to get a gram of gold. And we are talking about this kind of dilution. Um, and that, I think, it's an appropriate term, which is not, it was very common like 10 years ago, but now we cannot hear very often because our attention moved into some other things. But the idea is to detect or extract something very valuable from a huge amount of data. And so we're dealing with this dilution. This is most of the times the kind of problems that we have for machine learning, for in the context of uh, not accurately enough called classification problems. Sometimes it's not even about the dilution of the outcome, about the positive target when we're looking for profitable customers or fraud instances. Sometimes we deal with poorly known, poorly determined, poorly defined positive classes. Is no better is no better example than fraud, because fraud by its nature it's a problem of uh, the police and the burglar, where okay, fraud is not static. We try to chase and discover fraud, but there are fraudsters at the other side of the thing, trying to scheme you in a new way. And this happens, for instance, with I don't know, with um, uh, advertisement farms or spam farms. Spam is a good example as well, because it's some kind of deceiving. So the thing is that the the thing you want to detect, the thing you want to retrieve, it's not even known because it's dynamically evolving. Um, there is some active purpose of deceiving. So most of the times we do not even know about um, what are we trying to find. I I would say, for instance, for digging with this problem with fraud, when we come with a labeled data set of fraud, in the lucky case that we have one, um, we cannot tell for sure that these positive labels, these positive instances, are all that there are actually in the data set. In other words, we can have a misclassification problem, and for sure we have it, because I bet that there are some instances of fraud that are not properly labeled as positive, because uh, it's very difficult to get that at a scale. And if you want to deal with the problem, for sure, you want to deal with data at scale, and there's no reasonable amount of human annotators or human inspectors in order to process millions and millions of transactions or element instances, emails, whatever you want to call it, and, say for sure that something is not a fraud, something is not positive. It's probably that you cannot detect and flag all of them. Um, Even further, sometimes if you think, okay, my data is reasonably balanced, and say, okay, so not you are not challenging the data enough. If if you think that, for instance, you're trying to model some event in a funnel, in a marketing funnel, which is very common in e-commerce or advertisement. If you think that if you come up with a problem where your data is and your positive class is numerous enough, is balanced enough, um, and defined enough, probably simply you are not reaching for the top valuable um, use, instances that you want to detect and you want to identify. So, for instance, you say, okay, I have a very good balanced data set about people um, coming to the homepage of my website once I target them with a specific advertisement. I'd say, okay, the other side, maybe your problem is not challenging enough, because maybe you want to identify those customers not only going through your homepage, but going going further in your funnel, where you want to some more valuable outcome, which is more worthy, more meaningful for you, and obviously it will be less frequent, and it will cause a most more unbalanced problem for you. So even if your data is not unbalanced enough, probably is that your objective is not ambitious enough, um, or maybe the granularity of, of your problem setting is not fine enough, because maybe you can have as many instances as you need about the possible outcome, but you are not doing them in a granular enough uh, um, in a granular enough environment, which okay is not the same as targeting the getting identifying a customer which is going to end up in the end of your funnel, but maybe you want to do that separately for each of the um, channels that you have for advertise to the users. So um, if you go deeper enough and you go granular enough, you end up not having enough positive instances in that particular segment. So once again, is if the data, most most of the cases I can think of, um, if your data is not unbalanced enough, it's because your problem is not ambitious and valuable, and you're not looking for a valuable enough objective. Okay, so how we deal from the technical point of view with unbalanced classification problems, which, as we explained, is probably most of the times, if not always. Um, well, first thing, we do not do smote or resampling methods. And this is my top opinionated thing about all of this, because many people go for balanced learn libraries or smote algorithms and things like that. And this is what we are told in the literature and in many papers um, from the academic environment is the advice that we have most of the time. And, and I found only problems with that. If you let me the Chinese or the Zen quote, you do not try to put legs on a snake. Okay, so what does it mean for this context? When we have an imbalance problem, we want to move that problem into the domain which we are most of the time comfortable with, which is balanced data. But it's a denial of the reality. It's trying to get back to the place where you are comfortable. You think like when you move, you use your legs, and you think that, and there are animals which move very well, and the design is made for not having legs. And having legs for them will be a disadvantage and some uncomfortable thing. And when, in our case, when we are used and we learn from academia and from our academic um, curriculums that we want to balance data in order to have proper accurate metrics and things like this, and for the logistic regression model to comply with all of its assumptions, things like this. And, but we're dealing with something different, which different from our expectations, from our academic background. Um, it happens that we don't need to balance the data. So to get back to our uh, comfort zone, we got some more techniques. First thing is to acknowledge that. First thing is, I think this is better established. You need to look for appropriate validation and evaluation frameworks and metrics. So, well, I think it's commonly accepted that we do not use plain accuracy for unbalanced problem for classification. We can have many times um, F1, precision recall kind of evaluation. We can, we are free from threshold and we do not want to set the classification threshold at a particular level. We can think about precision recall curves and area, and these are the district curves, much better than classical rock AUC, because classical rock AUC it suffers from heavy imbalance. Sometimes both of them are measuring how well we sort by probability, and if we do little misclassifications in terms of ordering, when we try to rank this by probability or by score, but rock generally is not it doesn't focus very much in the top and in the top level predictions. So probably PR precision recall curves serve best to free from threshold evaluation of unbalanced data for classification. And another important thing, and something that sometimes if we do balancing and smote and things like that could be very misleading, is that when you do cross-validation or you do validation, you can find that your model performs very good on the validation set, but because this validation set is affected by the resampling methods, having a more balanced evaluation data set, obviously it's gonna to overestimate the metrics and the performance of your model, but it's gonna be detrimental for the actual functioning of the model. And you go to test or production data or inference time data, you realize there, if you're lucky enough, that the performance of your model is coming down off a cliff. And why? And because you validated and you optimize your model for an environment which is much less diluted than the things that you are using your model for. So if we're sampling very carefully with not evaluating and optimizing your model towards the balanced data, but with the natural rate data of the target. So that should be maintaining your validation and test data sets. As I'd say evaluation and validation first thing. What comes next? Well, if we're acknowledging that we're not doing classification, but anomaly detection, we should think about anomaly detection. So adding signals of anomaly in your data should be very useful. And I think it is, in my experience, doing adding detection signals. Sometimes people think about doing only detection, and if the score of anomaly is above a certain threshold, you classify this as anomaly. But I think it's more useful to use several signals and incorporate it into a model together with some other features, and have a more robust model with very strong signals for how strange or deviated an instance is out of the whole data set. And I think most of the approaches for dealing with unbalanced data comes from this. Anomaly detection, what does it mean? Somehow it's unsupervised learning, and it's okay to do unsupervised learning when you do not have enough data or enough labels. this is the case. We do not have enough labels. Our labels are not strong or solid enough because we can have some mislabeling, like fraud not being flagged as fraud. Um, you should not rely fully on labels as long as your labels are not good enough, or not good enough. And labels, it's always the limiting factor of models because it's very hard to acquire. So how we do anomaly detection? Well, there are full of set of algorithms there, uh, which save you the pain of doing smote or um, the self-deception of doing resampling methods. And anomaly detection shows allows you to measure yourself and the algorithm and your models in the real data set without doing the self-deception of resampling, which, okay, if we think about needle in the haystack problems, which are all of them, um, the smaller the haystack, the more easy the problem, and the greater your metrics are going to be. But you cannot deceive yourself and evaluate against uh, easier than actual haystack. So with anomaly detection, you get these flashing points for, okay, this is strange, and you do not rely that much in labels. How do we do anomaly detection? There are several methods. And for instance, we have the classical SVD, one class, singular vector, singular vector, no, support vector machines, one class, which is very common. And I don't like it very much. Um, singular vector, sorry, support vector machines are very elegant in their definition, but they do not scale very well. They do extra dimensions, so they're behind the scenes. They're complicating a lot of the problem dimensionality, which is sometimes great share of the problem. Mm, isolation forests, I think they work very well. They got all of the advantages of tree-based models and random forests in this particular case. They do not have any assumptions of the distribution of the numerical features. They deal with non-normal distributions. They deal with very naturally with unbalanced targets. Mm, what else? What else to say? There are some. I'd say those are the maybe top most commonly known, most widely known algorithms for anomaly detection. There are some other more personalized and creative ways of doing anomaly detection. If we think about um, any kind of gradient boosted trees algorithms, we can we can apply them in a non-supervised mode. We do, for instance, we try to fit a regressor, and we say that all of the instances have target, let's say, 0. We try to predict that. And the most strange or out of the distribution data points, they will have, in general, greater deviations from the expected target because they're more difficult to predict, more difficult to model, and they lay outside the distribution. And that is a pretty interesting way of doing that, and I found that it works reasonably well. So it's fitting a regressor, whatever it may be, but we can leverage the gradient boosted the gradient boost trees algorithms in order to do that. We fit a regressor on a fake target, which is 0 for everyone, and we can get an approximation of how strange a point is based on the error on doing this prediction. There are some other things related to that as well. For instance, um, discrepancy between ensemble of trees. And I'm talking most of the times about trees because are the models that I think they're more powerful and versatile. Um, for instance, if we feed a model with an ensemble of trees, and we found that there are some instances where the between the trees the discrepancy of the predictions it's very wide. We can assume that this data point is strange, is anomalous, because there is no consensus among the predictors for having for coming up to terms about if it is a positive or a negative. It's just strange. It's just not generate consensus and yields for the model different outcomes based on different perspectives and different models about this. So it's used sometimes in the context of active learning, um, where active learning we try to maximize the value of the labels, and we ask about we ask about labels for data points which has a great discrepancy between ensemble models or ensemble trees, and it's a strong anomaly signal as well. There are more things connected with this with deep learning as well. And even if we are in the context of tabular data, there's a role um, for deep learning as well, because another side of this problem with unbalanced is well, the key problem of all of machine learning, which is generalization and overfitting. You cannot um, fit a very complicated model when your data is scarce. And with classification problems, when they are unbalanced, and we say most of the times they are, we have a scarcity of data. And we should be very careful of not overfitting a complex model deceived by the fact that we have millions of data points, because maybe we have just a few hundreds of positive instances. And we can end up saying that that raining in the desert is it happens more frequently uh, days of the week where they have a T as a first letter of their name in English. I mean, we can overfit very easily if we use a lot of features for a model where the positive instances are very infrequent and very scarce. So how we deal with overfitting? A very good way is do projection and the project data and the features into a dense vector space. So we can think about autoencoders. Autoencoders, is, most of you probably know that they're these kind of non-supervised algorithms for deep learning, for neural networks. So we try to project and narrow down the neurons and the vectors and um, the layers and the dimensionality of the layers of the vector for for a data point across the okay. So after the intermission, we were talking about deep autoencoders. Deep autoencoders as a way of doing dimensionality reduction, which makes a lot of sense in the light of um, the high the high the frequent possibility of overfitting. Um, Deep autoencoders are a way of doing neural networks, fitting neural networks in an unsupervised setting, where the only thing we want to know is how to project into a into a vector space where we have a dense vector representation of the data, which is accurate enough, and we can distinguish one point from another, both in the natural or in the original space, and both in the reduced similarity space, in the projected space. It's like principal component analysis, if you like, but with the expressivity of neural networks. So the thing is that you narrow down the dimensionality of the vectors across the network as you go deeper and deeper. And then when we reach the top and reduce dimensionality, the less dimensions, you start going down and unfold again and expand the dimensions again and try to reconstruct the original features, the original variables of the data. Um, it works very well, and it provides, well, we can um, neural networks are infinitely expressive as long as you got data and layers and complexity of the model enough. So you can reconstruct anything and make things as compact as you like, as long as you have enough computation and enough data. So, um, but the idea is to do that in a careful way, in order to not to overfit to specifically the data that we have. So for that purpose, we have some of the kind of more sophisticated autoencoders, like variational autoencoders, which try to match not only the data itself, but a distribution of the probability of the features of the data itself. And you can go for that if you like deeper. But most of the times, well, depend on your case and where you, how much computation you have, and how big is your problem, and how valuable is your outcome, um, and your accurate predictions. You can think about how deep you want to go. But sometimes simply adding batch normalization and dropout is good enough to have a robust representation and very dense and very compact. What we have here is twofold. The benefit of this. On one side, we have the obvious dimensionality reduction, where we have very compact features, and they're more difficult to overfit in the supervised stage, because we do not have very high numbers of features where we can fit spurious patterns and lead to not generalizable models. Um, in the other side, we can have very good anomaly signals from out of the autoencoder by thinking about the reconstruction error. I mean, there is a difference in an error. We can think about root mean square error and things like that between the original features of the data point and the reconstructed version out of the neural network. We should make this as small as possible, as we do during the fitting of the autoencoder, but there are some discrepancies. And we expect the strange data points and the anomalous data points, the out of distribution data points, to have a greater error when we try to reconstruct them. And we can have a global metric about how big is the error across the features. And we can use this as a very strong signal about how anomalous is this data point. Another anomaly signal. We have with autoencoders two things: the projected dense dimensions, easier to fit, more difficult to overfit. And in the other side of the outcome of the problem of the autoencoder, we have this reconstruction error as an anomaly, very strong anomaly signal many times. So beautiful. What else can we say about anomaly detection? about this in the autoencoder. Um, we can go to very deep, very narrow autoencoders, uh, putting the representing these data points in a very compact space, and that will make inference very um, um, much lighter. The thing with deep learning, especially, is that if we if we advance computation enough in the training stage, we can save that later on during inference, which sometimes and many times is a bottleneck. We want to do real-time inference and things like that, or maybe we are trained against a few million data points, but then an inference, even if we do batch, we do need to uh, score 100 million data points, and you need to be very cautious about the costs in inference time, both in batch or both in real time, because of the scale or because of the latency requirements. So especially deep learning is very prone to do that, to move computation back and forth, and you can um, weight more the computation on the training on the training stage in order to have more compact representation of the data point. If you run for longer iterations, and then that cost is saved at inference time. So another interesting thing about deep learning for this, even if I'm talking most of the time in the context of tabular data, and so it is with this kind of autoencoders. But autoencoders, you can do them for images as well, but I'm thinking more in tabular data. And yeah, um, I wanted to think about these non-supervised approaches for um, for the anomaly detection kind of problems, because they 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 aim towards non-supervised, where we have a strong focus on the scarcity of the labels, especially for the positive class. And we can think about some of the things. Here is a huge jungle of many possibilities, especially with deep learning. We can think about contrastive learning. Contrast, I try to say it again. Contrastive learning. It's a very cool thing. Um, it tries to some. It looks some point it shares ideas with the autoencoder, because it tries to project things into a more compact space. Um, this space for the contrastive learning is special because it tries to maximize separability. Somehow, it's what it's trying to do, the supervector machines, because they try to maximize this margin and this separability between the classes. Contrastive learning it takes this one step further with deep learning. So we project things mm, into a more compact vectorial representation for generating embeddings, but trying to maximize them, trying to maximize the difference between different embeddings or different data points in the original space. So for doing contrastive learning, we take sometimes pairs of data points, and we say, okay, these two are different, and we try to feed the neural network in order to predict this maximization, and trying to keep the separability of the embedded representations and as it is in the original space. With autoencoders, it happened similarly, but we were not doing focus on this separability of originally different vectors. It was something more instance to instance level uh, approach in the autoencoder. We only wanted to reconstruct and being able to project. We want to project, go back and reconstruct, and have the vector or have the data point intact after that. In contrastive learning, we expect that if 2 points or if 2 data points are different in the original space, we want to project in a reduced dimensionality space where they are separated as well. And so sometimes we do with triplets, and we feed to neural networks a triplet of points, and we have an anchor, and we have a positive instance and a negative instance. So we say in this triplet that relative to this anchor, this is similar and this is not similar, and we expect to have that being able to detect and express that distances in the projected space. There are several architectures for this with deep learning, and one of the probably best cases for me, the best instances about this is sentence BERT. Sentence BERT tries to project sentences or parts of text, sequences of tokens, into a dimensional space where the projection of similar sentences are closer than the projection of different sentences with different meanings. And sentence BERT or SBERT is a very powerful library for natural language processing and for projecting text and dealing with text. And it follows this approach with anchors and similar and dissimilar and Siamese networks and triplets. If you want to dig that thread, sentence BERT is a great use case for that, for contrastive learning. Semi-supervised learning. We are acknowledging the scarcity of labels, and we cannot rely only on supervised methods for unbalanced data classification problems, which most of the time we can think that they are not classification problems, but some different kind of problems like semi-supervised learning or anomaly detection, or things that the key idea is that we want to think that, okay, we got cats versus dog images 50-50, and that is what we learn most of the times in our academic settings. And this is where we wanted to be most of the time, but that is the ideal case. And like Nicholas Nassim Taleb would like to say, this Platonism doesn't occur very frequently in our real life scenarios, and this idealization of machine learning as a classification problem is good as a mind exercise, but it's just a starting point for going to real case scenarios where we have very different environments, very much more complex problems than that, and trying to deny the complexity and the non-ideality of our problem at hand. And non-denying that is a first step toward a path of of less suffering, with very sometimes very hard and very interesting problems. So, did you get? Oh, let me take a brief look into a couple of to a few things that I wanted to mention the previous day in the last part of the video, which I totally forgot about that, but I keep on coming back to them. So I wanted to give them a quick look because I think they're very relevant for this topic about classification in the domain of unbalanced classification problems. And somehow uh, one of them is quite obvious, but specifically because of this, is because of being so obvious, is one of the most important ones. And this one is about the loss, the evaluation loss that we use during the fitting of the algorithm, the measurement of the error that we want to minimize during the fitting of the algorithm, which most of the times in classification is logarithmic loss, is cross entropy. Um, um, yeah, specifically when we're using gradient boosted trees and these frameworks like the kind those in XGBoost and the likes of them like IGBM or CatBoost, they come for specifically for this setting, for this problem setting, they come with very handy tools or parameters for doing kind of weighting in order to have some evaluation, some custom evaluation, some custom loss in order to focusing dominantly in the minority class. Um, and they have things like um, weight per class or this kind of parameters, which allow you to give um, simply weight more and ponder use a ponderation for modifying the loss in order to penalize harder the misclassifications in the minority class. So this is very effective when dealing with unbalanced data sets. There are even some automatic ways doing that. Sometimes you try to fit taking a look in the measurement of the overall fraction of the positive class. But there are, let's say, you can weight 1,000 times heavier, give 1,000 times more importance when calculating the loss to the positive class, to the minority class. They have even automatic ways of doing that, like balancing automatically or doing. It's very typical as well to do square balance parameter things cat boosted if I remember properly. Because yeah, one of the things that happen is that if you give too much weight to the minority class in the calculation of the loss, you can end up overfitting because the loss is driven by a class where you have so little instances, so few instances that uh, you're not going to fit a generalizable model. You focus too harder on that, and it could mask the difficulty of the problem with this, and end up in an overfitted model. Um, there are some other things about these custom or weighted losses. Um, not always, but sometimes you want calibrated models, calibrated probabilities. With calibrated probabilities, I mean, if you take the range of predictions within uh, zero point 0.7 and zero point 0.8, you want that not only to be a score for proper ordination, for proper ordering, but you want the ratio of the actual labels in that probability range to be something around the ratios that you have in the probability range. So they should be matching the proportions of the labels and the average probabilities. You take predictions as probabilities, and you want to interpret that. Sometimes you want to have that these kind of calibrated models when you you want to set a threshold, and this threshold for probability for classifying as positive or negative, you want to keep it across several situations in order to control how aggressive the model is being at classifying the positive instances. Sometimes you only need a proper ordering, so you only need something like given a high AUC, say precision recall or rock cure. So you only focusing on ordering, so you do not require the predictions to represent actual probabilities. It's just a scoring for doing proper ordering. So, but when you do this kind of weighted loss, the calibration of the model could be broken. So you need to track it with additional metrics like prior loss, or maybe you need to do on top of the predictions like an extra layer for the model for some isotonic calibration layers or things like that, which are available there, and you can. But you need to keep in mind that this weighting of the loss could disrupt the log loss standard function, which tries to produce a calibrated model with predictions representing actual probabilities in the case you need it. There are some other fancy custom laws, or not custom, but more specific for the case of unbalanced classification. And we can think about focal loss as well. Focal loss is a variation of cross entropy. But it takes into account the confidence of the model at predicting an instance as a positive or negative otherwise. So let's think that if the probability is 0.5 for the positive, 0.5 for the negative, we could interpret that we can assume that the model is not very confident for that particular instance because it's somehow ambiguous. This is taken into account into the loss, into the cross entropy, and it adjusts. If I remember properly, it adjusts the way of the somehow the learning rate. So it takes definitely some measurement of uncertainty and incorporated inherently into the calculation of the loss for fitting the model. And this comes from the realm of object detection, because we are in detection as probably a best word for unbalanced classification. Detection in object detection, specifically for images, um, that's where originally it came this specific loss for dealing with the confidence of the problem, and it's very um, it's very well suited for this kind of problems with detection and unbalanced classification. It somehow it connects with active learning, where we want to treat differently instances based on how confident or how difficult or valuable they are for the model, and how difficult they are to classify, or how hard is the consensus, or how how high the spread between the different models or different ensemble of the models are in terms of their predictions. If the spread is too high, we can assume that there's not great consensus, and we assume that this particular instance is hard to classify. The model is not confident enough, and in the case of active learning, we can interpret that this instance is very valuable in terms of acquiring a label for that. One probably last thing, and we could say more things about balanced classification object and the problem of detection of unfrequent things, or what I like to call these kind of problems, which are very frequent, and some, they're maybe more frequent that we want to acknowledge. I call them needle on the haystack kind of problems. Um, and it's about something which I have a very strong opinion about it, because I had, in particular, in myself, I had hard times and bad experiences with smote, and somehow I reject that. I reject that idea of synthetic uh, data, synthetic labels. It's like trying to think or try to mask that you have scarcity of information, and try to bootstrap information out of a very narrow set of instances, which happen to be the positive or the unfrequent class. It feels wrong to me, because uh, creating 1,000 instances about out of a hundred or 1,000 instances, synthetic instances out of 10 authentic or actual instances of the minority class. It sounds like cheating. But synthetic data is something that has become more reasonable and less crazy to think about. In the case of a smote, probably is not the case, because smote, um, mm, the versions that I know, there are a few of them. For instance, those based on near I could say it, nearest neighbors, and try to somehow interpolate between the synthetic generation and the actual vector space. I mean, um, against against the instances in the original vector space. This synthetic data generation is starting to make more sense as long as we have, um, or as we're finding better ways to have compact representations in the term of embeddings with neural networks. They're very useful and very powerful to map the actual instances in the full original vector space, map them into a very narrow, very compact representation, where we are, by virtue of unsupervised and semi-supervised learning, and the model is capturing the underlying structure, the mm, the latent space in which we can do things, and we can get deeper representations about the structure of the data. So if we do the synthetic data generation out of the latent representations of the data points, of the instances, um, simply saying disturbing the embeddings, um, it's a more reasonable way of doing synthetic data generation. You can think about data augmentation, and it's not a crazy thing, and it's found very, very useful for dealing with data, with scarce data. We can do synthetic generation. We do that as well somehow with generative adversarial networks. And yeah, it's more reasonable to do that if we are previously tracking and learning the latent representation. We got better understanding about the structure of the data. And on top of that, inside that, we do the the disturbing of the embeddings, and we get. I think it's a better way, and my experience is a better way to do synthetic data generation. I, I'm saying once more that you need to be very careful not to cheat yourself. For instance, you think, okay, I'm doing data resampling or synthetic data generation in order to learn better with only training data, and I leave aside testing data. And okay, you say, okay, this is robust, this is solid. We can do this. It's rigorous. It's a rigorous approach. And then you ending up doing cross validation inside the training data set, which is resampled, which contains a greater amount of minority sample. So you cannot do that in that way. So you need to be very careful with that. Okay, we got sorry. So this is what you need to do. Um, Synthetic data generation, it's okay out of Latin representations, out of embeddings. It's reasonable to do that. And well, that's probably the remaining things I wanted to mention. Um, um, yeah, it's just like a bonus on track on all the things that we commented about classification in the realm of unbalanced data set and unbalanced problems, and the problem of detection and needle in the haystack. So that's what I wanted to add, and I hope it's useful for you. So here we got the thing. I'd say complete for now. We could say some other things, but I think it's quite comprehensive right now. So I hope it's useful for you, and um, we could discuss about this for some more kind of problems. So hope it find you useful, and see you next time.